Quick question.
Oh, David, quick question.
Yeah. Recursion. Let's talk about recursion. I'm going to share my screen with you because I've got this amazing example of recursion.
Doggy.
Sorry?
Let me myself. Sorry.
Okay. Hi, doggy. Cool. So here's a recursive function. It's called say using recursively. Kevin, can you do me a favor? Can you talk me through what's going on here? Hi, Albert's dog.
Sure. So you've defined the function to take in a variable times, which is an int. You have the base case, which if the variable is ever less than 0, then it exits the recursive loop and it calls itself, subtracting 1 from the initial argument.
What do you mean by calls itself?
In line 6, you call the function again, passing in the argument times -1.
Yeah. So this is probably familiar to all of us, but it's okay if it's not. In recursion, you're calling that same function inside of itself to try to get it to do work. This is a recursive function, which is pretty cool because we didn't really have to do much. But what is this kind of, how could we have done this a different way?
As in iteratively?
Yeah. Also do it iteratively.
Maybe with a range?
With a range, yeah. Using, what would you do with that range?
And however many times would be in the function parameter, and that would be however many times you want to loop through.
Yep. Perfect. So we'd want to loop through a certain range of items. It's awesome. This is all we need for a recursive function, is we need a base case, which is saying this is when to stop. And then we need a function call. We need to call the function inside of itself. And so that's what we see here. It's just calling itself until it reaches the base case. Pretty familiar so far? Cool. Let's run this. You'd think with such an easy thing it would work. Cool. So we said do this 3 times, and it ran it 3 times because we said, all right, call this function, which has the times value 3 at the beginning, then check if times is 0, it's not, print this guy, then run the same function for times -1, which is 2. So call this whole function again. We say, all right, is it greater than 0 still? Yes, okay, print this stuff and then call it again. Now times is 1, still greater than this, prints this. Then we call this function where times is 0. Times is not greater than 0, so we just return and we stop. And that's the end of the recursive function. So the base case there, super important, because if we don't hit the base case, what happens?
Infinite loop.
Indefinitely.
Oh yeah. And that's when our playground starts to break and we all start to cry and we go home and say no more coding ever again. Let's rewrite this iteratively. So it's not 100% true for all functions, but for many, 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 many cases, you could rewrite that function from iteratively to recursively, from recursively to iteratively. Recursion will not get this deep into it, but in some special examples would let you account for a varying number of loops. So if there was a loop here, and then a loop here, that's 2 loops. We could set up a recursive function to have a dynamic number of loops. Not that important right now, but just know that we can make any iterative function recursive, but not necessarily the opposite. Can have recursive functions dealing with a varying number of nested loops. Cool. All right, Liana, can you walk us through how we could turn this say see you soon recursively function into an iterative function?
Yeah. You could have a loop that says a while loop that says while times is greater than 0. And then do for underscore in 1 to times. Print, see what you have up there. See you all at 2 p.m. for recursion.
Like that?
I think that's it.
Okay, cool. How many loops do you have here?
2.
Let me ask you, do you need both of them?
Oh no.
Okay. Let's ask other folks present. Do we need both of these while loops?
I don't think so.
Okay. Albert, why not?
While times is greater than 0 for I and times. Yeah, you could just use print. You could just put the print after the while.
Isn't it always going to be greater than 0?
It's always going to be greater than 0?
As you're saying, for the underscore in 1 to times, and times is starting at, I'm sorry, the thing is starting at 1. And so it's always going to be greater than 0. So I think the first loop is kind of redundant.
Okay. So kill this guy.
I guess you wanna, oh, never mind, sorry.
Yep. No, I'm asking around.
Well, you could get rid of the second loop.
Get rid of the for loop?
Yes.
Okay.
And then I guess you would decrement times after the print loop by 1,
Okay.
right? No?
There's going to be one more thing here. How can we make that work? Just because of where times comes from. And also, will you share your sandwich pizza?
Egg pizza.
Okay, cool.
It needs to be a variable.
Yeah, it does need to be something mutating, but why is it not mutating right now, this thing called times?
I don't know.
Is it constant?
Is it constant? It is a constant, but why is it, where does it get that constant value from?
Function's
It's the
parameter.
argument.
Say that again. Go ahead, anyone.
It comes from the argument.
Yep. This argument is constant.
So to get around that, we can save it to a variable,
Okay.
like var num equals times, and then num minus equals 1 in line 26. And while num is greater than 0 instead of times.
Okay, that's cool. Sounds good to me.
I guess you can also call the function inside the while loop and then like -1 at times. That work? It'll be recursive, right?
That would be recursive though. What are we trying to do in this function?
Just do it iteratively.
Mhm.
Can you scroll up for a sec so we can see the recursive one too? Yeah. So the difference, why we need a variable in the iterative versus the function is because when we exit the function, this many times gets reset. Is that what's going on?
Which function are you looking at?
The recursive.
So this is actually making another function call.
Okay.
Like what we can do is to see what times is, we can
Right.
print out times there. What it's not doing is what Kevin said, where we had to save a mutable value because we need to use that to make our while loop work. We could have used the for loop and possibly not needed that. But when we go and use the recursive function, kind of just like with our FizzBuzz this morning, we use this whole expression as whatever it returns, right? Minus is an operator. That's just a function call. So this whole expression just gets used as the next number smaller.
Okay. All right.
So let's go ahead and say at this instance, or at this call, the value of times is times. And let's see what we get. 3, 2, 1, 0. Cool. That makes sense, right? It just decreased each time. And we would see that the same thing here because we're just going through a loop. So loop and the recursion, pretty similar in this case. However, sometimes with recursion, our function calls might seem out of order. And then one of the prime examples is for Fibonacci. If you remember the Fibonacci sequence, it goes, well, depends who you ask, but it goes 0, 1, 1, 2, 3, 5. I don't know. Does anyone know how to make this into a program so I don't have to keep doing it by hand? It's getting harder. Anyone at all? Any suggestions?
Do you really want us to give you a program? Because I have one.
Yeah, let's start making one.
Oh, no, that's something different.
Oh, well, let's make.
It's the prime numbers, right? No, it's.
So what is Fibonacci?
The next number in the sequence is the sum of the previous two numbers.
Value of the next number in the sequence. Sequence is the sum of the two prior values, two previous values. Previous two values. That's how English works, I think. Previous two values. Something like that. Cool. Let me move things around on my screen. So that means typically when you're looking for Fibonacci value, you are telling you're looking for the term, which is an int, and you're going to return the value of that term. We've seen this before, right?
Not recursively.
Oh, we can do it recursively. It's just like turning around an iterative one. What would be, if we're going to do this right?
You have to do 2 vars to hold the values.
What are the 2 setup steps or the 2 sections of a recursive function? Second is call ourselves.
The base was the first.
Yep. What is the base of this sequence that we see here?
0.
Account for 0th term. How would you do that?
I mean, I don't know of any negative Fibonacci, so it would always be 0. Just set it a variable to 0.
For a term being negative or 0. Cool. How can we do that? What would we return in those cases?
I don't get what term is. Is term saying like what number we want up to, or is term the starting number?
Term is saying if I want the 8th term in the Fibonacci sequence, that's 13 because 1, 2, 3, 4, 1, 2, 3, 4. So kind of like an index, but it's mathy, so we call it a term. We also start counting with 1.
So do you just want to guard against the term being 0?
Yeah. Well, let's just say it should be greater than or equal to 0. Else, what happens?
Just return, like just exit the actual function.
Yeah, we could do that. But we do need a return value. Let's just say it's 0. Let's make up a rule here and say everything prior to the first term is equal to 0. What about the first term?
The first term is always going to be 0 or 1.
Well, let's think of these as a sequence. Let's subscript them. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. When I say term, I just mean which number, like if I was counting along the sequence, which one is it? Is the first term is above it, second is above that, third, and so on. So if I want the first term, it's always going to be 0. That means I can just say, if the term you're asking for is 1 or less, I'm going to give you 0. Or another way to say it is guard that the term is greater than 1. How do we feel about that? Okay. What can we do next? And this is the super important thing that Anthony told us. Kevin, what can we do with our code to say the value of the next number in the sequence, so the one we're looking for is the sum of the previous 2 values?
I'm not exactly sure to do it properly.
Okay. Well, let's start from the end. I'm sorry, the beginning. That's the opposite. If we start from the beginning, we saw the very first term is always equal to 0. What about the second term? Can we use the previous terms to create that second term?
Yes, we have to with Fibonacci, right?
Well, what we want to do
Oh, well,
is,
not
in order to figure out the difference between what's a base case and what's part of the sequence, we just try to apply the pattern of the sequence to it. And that's how we'll know when we're actually using it. So for the first term, we just kind of had to make up a rule and say, if you don't get anything that is larger than 1, you have to just provide me with the value 0. Now,
I'm confused. I thought the term was the was like the index almost.
it is. So if I'm looking at the first index, since it's a sequence, we start counting with 1.
Okay.
And the value there is 0.
But you're asking if we can use the term to add to give us a value? That's where I'm confused.
No, I'm saying, when I say term, I'm just saying look in this place. So if I say look at the second term, the value is 1.
Got it.
The actual number there, yeah. So if we look at the second term, so the number 1, which is the second term, Kevin, stay with me. Can we use the terms before the second term in order to add them up and get 1, or do we have to set up another base case?
We have to set up a base case for if it is 1.
Okay. How do we do that?
If term equals 1, return 1.
Yep. I'm just going to do the reverse of that. A guard statement in line. But are you talking about the second term, or are you talking about this value 1?
The value 1.
Okay. So we'll want to keep talking about within here. The weird thing is going to be, think about this like Tia was kind of alluding. Think of what we were looking for in terms of index, but return the values for those indexes. So if term is 2, which is all it could be, because if it's greater than 1 and this guard statement isn't hit, it's bigger than 2. If term is 2, return 1. So if the second term is what we're looking for, give us the value of that term.
Okay.
The reason I'm holding these as guard statements is just syntactically that makes things cleaner. The way you explained it is perfectly fine. If term is that, return that. Guard is just the inverse of an if. Saying, make sure this isn't true right now. But if it is, return, do whatever's in that else block.
Okay.
Cool. All right. Going to help me with the next number. I've got 2 base cases so far. For the first term, I would return 0. And for anything smaller than 1 as the term that's being asked, which typically doesn't, but it's good to account for, it'll also return 0. For the second term, I return 1. What about the third term? Can I start to apply the Fibonacci sequence?
We don't have anything holding the values yet, so we can't add them up, but those numbers are there.
So yeah, so those numbers are there. The numbers we need to set the base, to set up the base, are there, our base cases. And so the thing we're going to do with recursion here is it's not going to save any values. It's actually just going to call functions until it reaches the base case. It's weird, but it actually looks pretty elegant. If I am looking for, let's do a tiny bit of algebra here. I'm sorry, I really do apologize. If I am looking for the third term, what is that the same as calling recursively? If we're just applying Anthony's pattern up here, the value of the next number in the sequence, the sum of the previous two values.
I'm sorry, can you ask that one more time?
Yeah. So the Fibonacci sequence can go technically infinitely, I want to say, because all it is applying this pattern that Anthony stated before, that the value of the next number in the sequence is going to be equal to the two values that were before it, equal to the sum of the two values before it. So we walked through this a little bit. 1 + 1 is 2, 2 + 1 is 3, 3 + 2 is 5, 5 + 3 is 8, 8 + 5 is 13, and so on and so forth. Let's pretend we are not even looking at that stuff. How do I get the third term in the sequence?
Would it be term -1 plus term -2?
Yeah. So if I'm calling recursive fib on line 41 for the term 3, what functions could I call there to give me the same exact thing?
On 41?
Yep. That's the same as blank plus blank.
Yeah.
There are two function calls.
So when you just called recursive fib, and then put term and then term -1, and then on the other, what?
Yeah.
Term -1 on one side and then term -2 on the other side.
Cool. And to do it just specifically for 3, what are the two terms that I'm using here?
3 - 1 and 3 - 2.
Cool.
Okay.
Perfect. So calling recursive fib for the term 3 is the same as calling recursive fib for the term 2. And then just to hammer it in, Albert, if I'm calling recursive fib for 5, what is that the same as calling?
Would be recursive term 2 and plus recursive term 3.
Like this?
Plus recursive term fib term 3.
I think these follow a little bit of a different pattern. If I said, what would the pattern be here? Why'd you choose 2 for this term?
Because it's 2 plus 3. That gives you the term 5.
Okay.
We have to follow the terms 1 or not 2, right? I don't know what these numbers are, the term numbers are doing here. I'm a little lost.
Sure.
Yeah, I'm lost too.
Term is still just what place in the sequence are you? So if I said, give me the third term, that's the same as giving me the second term plus the first term. Where if we look at our sequence and I say, I want the third term, that's the same as whatever the value of our second one is, which is 1, plus the value of our first one, which is 0, and that's how we got 3. Now to apply that same pattern, if I want to get it for the fifth one, I'll go and I'll look at the one prior, so the fourth term, and get back the value 2, and then add that to the third term, which is the value 1, and that's how I get 3. And then that's how we build our sequence. So if I add the sixth and the fifth term, or 5 plus 3, I get back the value 8, and that's the seventh term.
Well, we're not doing any of that work in the function.
No, but we can be just by recursively calling our function. And that's why we're going to start with the base cases. And then once we find a pattern to apply, we can start to actually lay out how the recursive call works and not have to do that math for ourselves, which is ideal. So Albert, in the example we were looking at, in order to get the fifth term, we just need the fourth and the third term. And here we got the third term. We figured that out. It hits a base case at 2. It hits a base case at 1. And we add those two together. And that's how we knew the third term was 1. What I don't know for the fifth term right now is that term number 4. We plotted it out here. We looked at it, and that's great. And that's helpful and all. But this is going to need to call itself yet again because it doesn't reach the base case. So if we were to call recursive fib for the term 4, that would be the sum of the term before it and the term before that. This whole thing that I have in parens is recursive fib for the term 4, because that's not something we've calculated. We have to go and we have to say, hey, does this hit a base case? No. Well, then we're going to have to keep calling that same pattern. And our pattern is call the function on the sum of the two prior terms determined by the function, which is terrible, a really annoying thing to say, but all we mean is return whatever happens when we add term minus 1 and term minus 2.
Yo, I'm so lost.
I know, it's great, right? So
Well,
let's go ahead.
That part I think makes sense because you're saying, hey, what are the two terms? You know, I feel like term is such a horrible word, but what were the indexes of the one prior to what we're looking for and the 1, 2 prior before the one we're looking for. And that's where the 1 and the 2 are coming in. And then that's going to give us our number.
Yeah.
Okay.
But the important thing to note is, like, if I am just, so I'm going to rewrite this. I'm just going to start calling it F, so it's shorter. If I am looking for the recursive fib for 6, I need to determine the recursive fib for 5 plus the recursive fib for 4. And if neither of those are our base cases, then what this becomes is
It has to work its way all the way down to the base case.
Yep. So recursive that and that plus the recursive that plus that. So this whole thing is the recursive sum of 4, and that's not even determined yet. Neither is this. So then we have to say, oh, okay, that thing, well, the recursive of 4 is 3 plus recursive of 2. And then I have to add that to f of 3. Isn't this great? F of 2 plus f of 1. And this whole statement is just putting together the call for 4 plus the call for 3. Let's space these suckers out. And then I still got to do the other side here, which is f of 2 plus f of 1 plus, and then finally, mercifully, we do hit a base case. So here we can just say, well, you called this function for, well, the second term that gets us back the value 1. And then, amazingly enough, we could do that right here as well. We could do that right here. Do that right here. What do I get when I call recursive fib before the first term? What's
0.
returned? Cool. And that's 1, and that's 0. And so on and so forth, forever and ever and ever. But I still have to keep going. Over here. So I keep recursively calling it. And that's a pain, a little bit, right? Who can simplify this for me? What is this guy equal to?
Wouldn't it be 0 plus 1?
Yep. So that's actually a really important point that Kevin brings up. It's 0 plus 1. So even though, or 1 plus 0, even though we know that the third term, or when we recursively compute the third term, we get back 1, this is going to keep executing until it hits its base cases. So it has to call f of 2 and f of 1 to realize that it has the values 1 and 0. And then in the end, every recursive function for Fibonacci, we actually just end up adding 1s and 0s. Every time we reach the base cases, we just add 1s and 0s. And so we find out that the sixth term is the sum of all of these 1s and 0s, which is how many? Just adding up this line.
5.
5, that's right. So the sixth term is just 5. That's recursion. So I know it was really nice to see it up here where we called a function inside of itself, but the whole purpose of recursion is that we saw a pattern for how a problem gets solved, and then we just decided to apply that same pattern until we got the result we wanted. So for Fibonacci, there's one rule. A value is going to be equal to the sum of the two values before it. Except for these two cases where we're looking at the first two terms, that pattern applies indefinitely for as high of a term as we'd like to. And so that's great. But what's the cost that we're seeing here? Besides that, it looks really complicated to write down. What are we doing a lot?
A lot of function calls?
Yeah. That's right. We made a lot of function calls. And further, if you look at like line 53, it'd be really nice to know, if I look at 53 and 54, it'd be really nice to only have to calculate the third term one time. We made a lot of function calls and we made, oh my God. Hold on one sec. Hello. Thank you. Made a lot of function calls and a bunch were duplicative. F of 3 is the same every time, right? Every time I calculate the third term, it's always going to be 1. But also, I'm going to calculate the third term pretty much every time recursively something larger than the third term is needed. So if I need the fourth, I need the third in order to build it out. If I need the fifth, I need the third. And it also takes the fourth, which needs the third. And all of that is a huge pain. Is there a way we can optimize that?
Can we change our second base case to include the third term? Return 1 for it?
Yeah, we could do that. We could say, make sure term doesn't equal 2 and it doesn't equal 3. It's the same as saying, see if it's 2 or if it's 3. Logic is amazing. But then what if I was looking for fib of 7? I think we'd still have the same thing for the fourth one and the fifth one and the sixth one. What's like, has anyone ever heard this term before? Or seen it, because I didn't even say it aloud.
Yes, but I completely forgot what.
Okay, cool. Anyone else?
Yes, but I also have no clue what it is.
Okay. What is this word? In English.
Like a note, something recorded? Yes.
Yeah. Record something, make a note. Cool. Memoization is really just recording the results of our function calls in recursion. So what I might do is, I might say, the first time I look for the fourth term of my recursive Fibonacci solution, I might put in a dictionary dict of 4 is equal to, well, what's the fourth term? Oh, cool. I might put in just some memo, some dictionary there, that if I am going to call the function Fibonacci for the fourth term, or for the input 4, the result is 2. And all I'm doing is keeping track of inputs as keys and values, or outputs as values. So this is a way that we can speed up our recursive solutions, because instead of having, let's say, for example, if I said that dict of 3 is equal to 1, if I calculate that here, because as we'll talk about with trees, there's an order in which these functions are executed. But if I figure out f of 3 here, then the next time I see it here, I can just say it's 1 if I go and I look at my memo. And the next time I see it here, I can just say it's 1 if I go and I look at my memo. And that's great because this is an O of, what does it cost to look something up in a dictionary?
Constant.
Mm-hmm. Looking it up is O of 1, and it just stops the recursive call in its tracks. So that's the way we would speed it up. How do we feel about this so far? Cool. One other thing I want to point out here to keep in mind, you see this a lot when you make a boo-boo or when you have an infinite loop. But what we have to keep in mind with our recursive functions is there's something called a call stack. Has anyone seen a call stack before or heard of it?
Yeah, in our single app projects,
Go ahead.
it's just the order that functions are called.
Yep. Order that functions are called. And it's a stack. So which thing do you think is always the next function to be called?
Recursive fib.
Yep. But if I have a stack and I am the part of the program that says, all right, time for me to call a function, where do you think I look on that stack in order to know which function to call?
The first function.
Yep. So it's a stack. What part of the stack can I look at?
The top.
Yep. At top. And let's talk about that call stack real quick. So if I want to do fib of 5, recursively, what's the next step here? Do I know either of these as a base case?
No, so you'd have to call it for 5 minus 1 and 5 minus 2.
Cool. And then Albert, do I know either of these as a base case?
No.
Cool. So what should I do in order to get there?
David, I'm super lost on
Okay.
like recursive. Try to see what you're trying to do.
Yeah.
But yeah.
So what are you trying to do?
Trying to find the Fibonacci order before the number you inputted.
Okay. So what do you want to do next?
So 4 plus get that, you want to get the previous ones, which is like 3 and 3 will be 2 and 1, maybe 1 and 1, or 1 and 0, something like that.
Yeah, but what's just the next step? So the pattern that we're doing here is for each function call, we want to call the function for 1 fewer and for 2 fewer. Let me make some space for us. So let's just looking at line 69 for f with the input 4. Is 4 either of the base cases we came up with?
No.
Cool. So then if it's not, what do we do?
We get 3 and plus 2.
Yep. Perfect. And then what about over here?
For 3?
For 3, yeah. Is 3 either of our base cases?
No. Be 2 and 1.
Awesome. Now, Albert, stay with me. Let's look at line 70, and then below it, if these are a base case, we will just put the value, but if they're not a base case, we'll put what the next recursive call is. So is 3 a base case?
Yes, it is.
Okay, cool. So what did we say it is? Actually, I'm gonna remove this because it kind of just takes a little bit of the elegance out of it. Let's say 3 is not a base case. That could have been one change we made. If 3 is not a base case, what can we do?
Then you have to like go again until you hit the base case. So it'll be like F will be like F. I don't know, David. To be honest, I don't know.
Well, just apply, look right here. Just apply this pattern.
It'll be the
Term is
term
3.
minus 1, then term minus 2. So it'll be 1, and then the one would be 2, and then the other one would be 1.
Cool. And then what about the rest of this? Is 2 a base case?
It is.
Cool. And that value is 1. Sweet. And then this, the value is 1. Then this, the value is 0. Then if we go through it like we did before, just gonna add all these guys up. Just like that. And so recursively, the 5th Fibonacci term is equal to how much? It's not 5.
1 plus 1, 3. 3?
It's 3, that's right. So we figured out this is 3, but I wanna list out what the actual call stack is. And this takes some very important fundamental stuff about functions. So looking at this function, print 6, func, print 6, print 6. Pretty good function, right? Pretty awesome in my opinion. If I said in here, print 6, what's gonna happen again?
It's just gonna print, it's gonna call the function again.
Yep. Keeps calling itself. And so what does this result in?
Infinite loop, infinite, never.
Yep. And that's again because we need it to terminate. But it's also, the reason this actually occurs is because for the first time I call the function, let's call that A. The function call isn't done until anything happening inside of it is completed. And so what that means is if this function goes, so when it goes and calls itself again, I'll call this function call B, A is not complete until B is complete. But then, of course, B is going to call the function yet again. That'd be function call C. And B can't be complete until C is complete, but then C calls itself, and then there's just, it goes forever. And that's why we get an infinite loop. The infinite loop is because the function is never able to actually finish its execution. There's no stopping point. And all those calls get moved onto the call stack. So the call stack says, what am I going to do next? Well, we started out with A. We started out with A. So if I say print 6 right now, there's a function call A. It's probably not called A in memory, but then A calls print 6, and then B is on top of that. And this is our call stack. Call stack. So then B is the next thing trying to execute, but it calls another function, and that gets pushed to the top of the stack. And then C would call itself, and that would be D. And at no point does any of these function calls terminate and allow us to pop the function off of the stack. That's what an actual infinite loop is. It's when a call stack never pops until it's empty. So when a function is completed, literally reaches the end of the block of code, it can be popped from the call stack. Our infinite loop here never removes anything from its call stack. It just keeps adding new function calls, and so on and so on and so forth. And at the bottom is the original function call, which is A. So the first time we called our function, any functions being called inside, excuse me, any functions being called inside our function are pushed on top of the stack to be executed before ours. That makes sense, right? If I have a function where I say add something and then divide it, I want the adding to occur, then I want the dividing to occur, and then I want the function to say it's complete. Should we make that function real quick? Add, then divide. Add 1 is an int. Add 2, an int. Divisor is an int. Let's say we return an int. Say var. No. What's it called when you add things up? Is it a product?
Sum.
Thank you. Damn. Oh, well for that. Thank you. Plus add 2. And then if we say return sum divided by divisor, we've got 3 functions happening every time we call add, then divide. Right? What are those 3 functions? Anthony, what are the 3 functions being called every time I call add, then divide? We lost them.
No, I'm here.
Okay.
Okay.
Hey, Scary.
Functions being called.
Mm-hmm.
Sum divisor.
Sum.
Really
What's that?
Sum and divisor in the function, is Isn't like a sum just a property?
Sum is a property, but work is happening here, right?
Right.
And then work is happening here. Oh, I love that. And so whenever I call add then divide, I'm doing addition, I'm doing division, and it also just needs to resolve the function called add then divide. Isn't this cool? Don't we love call stacks? No. All right.
So the three functions are you're adding it, which is going to be the add 1 plus add 2. Then you're doing the dividing from return sum divided by divisor. And then finally, you're completing the actual add the divide function.
Yep.
Okay.
And so our call stack initially looks, sorry, go ahead.
No, that was it.
Okay. Yeah, exactly. And in terms of what this does to a stack, we start initially by calling the function. Our call stack has that. Then when we try to add, our call stack looks like that. And then after we've pushed the addition operation onto the stack, it's got that. Then when addition is complete, it looks like just add then divide again. And so we just keep going through until we can complete add then divide. But oh no, we have to do division. So to divide, we push that, add, then divide. And then finally, we finish dividing. And lastly, we finish this entire function and our stack is empty. So why do I bring all this up? Well, for something like a Fibonacci sequence, what we begin to see visually isn't really a stack, right? What does this kind of look like in terms of data structures we've seen before?
Tree.
Looks exactly like a tree, right? Our recursive calls look like a tree. They don't occur in that way. So if I look at this guy, what I need to do is, nope. I need to first execute all the way down the left side of the tree. So I can't do multiple things at once. I can't do these different levels at once. And instead, I need to first to execute f of 4, well, I need to complete f of 3. I need to complete this recursive fib. Until the first recursive call resolves, I don't even begin the second recursive call. Because if I want to treat this whole line like one expression, I need to resolve this entire value before I can try to add it to this value. So I need to be calling and getting back some value for everything recursively happening down this left side before I can even begin to evaluate the right side. And that applies every recursive call I make for this Fibonacci sequence. Who can tell me back what I just said? Hello?
What I'm guessing you're saying, I did walk away for a second, but is you're saying that it can't perform the function at the top until it has worked its way all the way down and performed the other functions?
Yeah, that's definitely true, but there is a specific order in which they're going to get called as well.
What do you mean?
So like, go ahead.
Is it going to be from the leftmost side?
Yeah, so it's going to be on the leftmost side. So for us to recursively call Fibonacci of 5, I inline here in my functions definition say it's going to be, well, it's going to be recursive fib of 4 plus recursive fib of 3. But think about this almost like order of operations. This doesn't have a value until it's reached the base case and added up all of the like recursive sum that it needs. It doesn't even get to here before this entire recursive call is completed. And so what that means visually is that I can't even add up f of 3 until I've added up f of 4, which I can't even do that until I add up f of 3. And I can't even do this step until I complete this step. But that step's not completed. And then I have to go down. So you stay all the way to the left on the tree. You stay with the leftmost function call, and then it resolves up from the leaves.
So are you saying that this won't work because of the call stack, because it will never complete?
No, it'll definitely work, but the call stack isn't that first I call f of 5. It's actually, in order for f of 5 to be completed, everything else has to be completed first. So the call stack looks something like this. If I've got f of 5, then onto it goes f of 4 and f of 3. And neither of those resolve f of 5. F of 5 is waiting for both of these to be resolved before it can be resolved. And then on top of that goes f of 3 and f of 2, which are the recursive calls for f of 4. So each time I do it until I finally resolve something. So f of 2, even though it's the base case, it hits one of the base cases, I have to resolve f of 3 first. So f of 3 is f of 2 and f of 1. And then these two resolve, which allows us to resolve this one, which allows us to resolve this one, which allows us to resolve this one. So it's taking an intermediate sum, and then all of that gets added up, and now we have 2, right? So f of 4 is 2, and then we can finally say, all right, I've got 2 as the value here. I'm no longer making any calls there, so all those calls go off of the stack. And what I know so far in f of 5 is 2 plus whatever goes down the right side of the tree is going to get me my answer. So each time we make a recursive call down this tree, what it's actually doing is adding those function calls to the top of the call stack. And so in order to resolve anything, I need to resolve the recursive calls below it until I hit a base case. If we didn't have any base cases, we would never hit a stopping point, and our call stack would just keep growing and growing and growing.
Explain one more time. So on line 137, it's calling f of 5 first, and then it's adding 136 after. Why is it 130? Sorry, why is it f of 3 and not f of 4?
Because that's a great question, and it's like literally because of the way we wrote it. So check this out. I said that I want to check it for n minus 1 or term minus 1 first, as opposed to term minus 2. So that means that this guy's got to get resolved before I can go to the other one. So this goes to the top of the stack because it's literally the first thing appearing in the line. It's just reading it left to right on this line.
But if it's the first thing that's going on that line, then shouldn't f of
Yeah, f of 4 should be up 132 now. Since it's
No.
doing, isn't it doing the term minus 1 at first, which would be 5 minus 1, which is 4?
Yes. And so this is the top of the stack. I guess I'm not sure what you're asking.
I think I'm just thinking about it in the way that it's adding it to the stack. So how I was imagining it is you have f of 5, so that's going to be placed in stack first. And then the next term is going to be the term minus 1, which is going to be which is going to be 5 minus 1, which is 4. So then I was thinking it would add 4 to the stack next. And then it would do the other stuff. But it looks like it's 3 that's added first, which is term minus 2, as opposed to term minus 1.
Yeah, because what it's kind of going to do is, this is a good way to visualize it, but what it's going to do is it's not going to, the way we're talking about it right now is not actually how it's computed. It's not even going to see f of 3 until it resolves f of 4. But f of 5, basically by making our recursive call at that line, we don't end up with this. We don't say that, okay, I called f of 5 and that's just made up of f of 4 and f of 3, specifically because if I call this function for f of 5, then it doesn't actually finish its execution until everything inside of it is cleaned up. So that function stays at the stack. Then at the next step, a similar thing is true where f of 4 and f of 3 both need to be called in order to complete f of 5. But f of 3, we can't even begin to start executing until we've finished executing f of 4. And so when we call this, it's just going to add all the recursive calls that it needs to resolve as quickly as possible. So we're creating an intermediary step where before the right side starts executing, we need to do the entirety of the left side. So f of 3 is going to be the next thing called after f of 4. The right side is going to start triggering right after the left side. But for the left side to get there, we first need to do all the things inside of that. So I need to completely resolve the left before I can go to the right. And if we did this for a bigger number, it would work for any like subsection of the tree where I need to resolve everything on the left solely because I wrote the thing on the left as the first thing to be resolved in my function.
Okay, that makes more sense now.
Yeah. And that's entirely, again, because in order for any function call to be complete, it has to complete everything inside of it. So if I call f of 5, it's not done until every call that came as a result of calling it is done. Amazing, right? Maybe. So then the left resolves, and then the right adds its leftmost thing first, and then its rightmost thing, then that resolves, and then f of 5 finally has 3 from the left, and 2, nope, sorry, 2 from the left, and 1 from the right. And then this is our entire call stack. I wish there was a way to color code this. Maybe I'll write it out and push that up somewhere. But if you look at this, the inverse of the tree is our stack. The left side will resolve, and then the right side will resolve. How do we feel about this look at recursion? Everybody come back on camera.